Hi, welcome to my second lab where we will be exploring the motion of a falling object. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly down, meaning slower than a rock dropped from the same height. Today we will be using a tracker to track the height, position, and time of our object and a computational model through GlowScript to explore the effects of gravity and drag present. We will be later comparing these models to draw our own conclusions through the application of physics principles. The physics principles that we will be applying today include Newton's second law, the momentum principle, which states that the net force is equal to delta P over delta T. In other words, momentum is equal to mass times velocity. We know that an object falls to the ground has a non-constant velocity, which means that the net force will not be equal to zero. We know that there are various forces that are acting on the falling object, such as the force of gravity and the force of drag, which is a force acting in the opposite direction of relative motion. The equations that we will be applying today include the position update formula, the velocity update formula, gravitational force, and drag force formulas. Each force being applied will have to be multiplied by their direction. For example, in gravity, we would have to multiply by j hat since we're moving in the y-axis. In the drag force formula, we will still have to multiply by a similar v hat that identifies the velocity of its direction. The b in the drag formula stands for the proportionality constant, and the v stands for the object speed. For the tracker analysis, I used a video of a falling, crumpled up piece of paper. Here we can observe the video. I started this process by extracting motion data from a video of an object. In my case, this object is a paper ball in free fall. To analyze the recording and extract data, we have to upload the first recording to a tracker. First, we need to specify what is the length scale of our object, and we set it to 2.5 centimeters. And we studied the coordinate system, going frame by frame, finding the center of mass of my object in the position axis, such as the ball will move in the negative y direction, since in this case the object is falling and going downwards in the y axis. To obtain the full position versus time graph, we have to manually select the center of mass. And looking at the graph, we can observe a negative non-constant increasing in a magnitude slope, which demonstrates that the paper ball is falling with a non-constant velocity in the negative y direction. This is the graph that I constructed using Tracker. Later on, using GlowScript, I was able to code a computational model that compared a falling object without a drag force and then one with a drag force. Here we can see the comparison between the one without and the one with. We can easily see that all the major when we compare our two models, the one that has a drag force and the one that doesn't have a drag force, we can easily see that all the major point of the graphs are almost the same. Here we can see how the computational model that was made with GlowScript. And when comparing these graphs, we can easily see that all the major points of the graph are almost the same. However, there could have been a slight error that could have been done. We can conclude that the three models match our experimental observations, and we know for the terminal velocity, the magnitude of the drag force equals the magnitude of the gravitational force, meaning the net force is equal to zero. Also, the model without a drag force never reached the terminal velocity because the gravitational force is never equal to zero. This is the analysis of the drag, and it states that the forces increase as velocity increases until terminal velocity is reached. And what does this mean? We're going to be examining the velocity versus time and predicting the time models. In the graph with no drag force, the term of the velocity is not reached as it is constant velocity, so there is no terminal velocity. Meanwhile, in the other graph, we can see the velocity is increasing in a negative constant direction due to this drag force. And what if it wasn't equal to zero? Then our delta V would still be almost zero since it would be 0.99.